Okay, we are going to move on to section 5.3 in this video. The previous video, we were just being introduced to polynomial functions. We learned kind of what the disqualifiers were if you were ever given a function and asked to say whether it is or is not a polynomial function. Looked at adding, subtracting, multiplying those, and then spent some time on some exponent properties. What we're going to be focusing on here today is really examining the graphs of polynomial functions. I just have as a review at the top of the notes page here. These were our four kind of disqualifiers that what you're looking at is not a function if it contains radicals, variables in the exponent, has any fractions as the exponent, or you'd notice a variable in the denominator. Negative exponents in the numerator also are kind of the same thing as this, okay? What I would like to just focus your attention on first is in this first box here, I want you to be comfortable with some of the special names, particularly what's in this column right here, for polynomials. And so what I have for you here are, down this column are specific examples. Okay, this column tells you the degree. This tells you the lead coefficient, which I have pretty much in green. The 6 would be the lead coefficient for this. And I want you to make sure that you're comfortable associating the name of the polynomial with the degree. Okay, so if you just have a constant, okay, no variables at all, that's what the name would be a constant, and the degree would be 0, because the idea is if you don't see a variable at all in your problem, then the assumption is that the exponent on that variable was actually a 0. We learned yesterday then in that video that anytime anything has 0 as its exponent, it ends up reducing to a 1, and so that's why that must have been the scenario here with this, and so we just call that degree of 0. If you recall, degrees are supposed to be the highest sum of the exponents on your variables for any term, okay? And so you can see here that the highest sum on this would be a 1. So this is first degree. The name associated with first degree polynomials is linear. Okay, you probably heard that term before because the graphs are these straight but non-vertical lines. Now, if your degree is a 2, meaning the highest exponent that we're seeing is a 2 here, we call those quadratic. Okay, we had spent a whole unit talking about quadratics. So far, these names should sound pretty familiar. If the degree is third degree, we would call it cubic. That should sound like it makes sense. I think the one that's the most difficult for people to remember is when the degree is 4. The specific name associated with fourth degree is quartic. A good way to kind of memorize that is if you think of a quarter is always a fourth of something, whether you're talking about a coin or just a quarter, or a portion of something, it's always a fourth. Okay, so if we're talking about the degree being 4, then we call that polynomial a quartic. Quintic is fifth degree, and once you get past fifth degree, anything higher than fifth degree, like for example here that would be an 8th degree, then you just are kind of generic and you just say, okay, there's no special name, but we just call it 8th degree, okay? So what I'd like for us to do first, before we spend some time looking at these graphs here, is this is just asking us to simply state the degree, state what the lead coefficient is. That's assuming if you were to rearrange it in descending order, what would be that front number. And then it says if it's not a polynomial in just one variable, meaning if you're seeing multiple types of variables, I don't really understand these directions. It says explain why. I don't know what the explanation would be. If you're seeing multiple variables, it's because there's several variables there you're looking at. So let's go ahead and look at example A. Okay, we want to be careful. These aren't always in descending order. We want to glance, make sure we've got it in descending order. I'm going to look at that highest exponent, and I'm going to use that. It's a 5. That lands me right here in this chart. So I'm going to call this a quintic polynomial. Okay. It's a quintic polynomial, and then I'm going to abbreviate here LC for lead coefficient. The lead coefficient would be the 8. Okay, here is a situation where I'm seeing multiple variables, so I'm just going to simply circle it and say, okay, there's 2 variables here, and they they told us that if it's not a polynomial consisting of one variable, explain why. Well, I'm circling there and saying I'm seeing two variables there. Okay, let's go ahead and jump over to this last one. Now be careful. You'll notice if you look closely, the highest exponent's not a 4, it's actually an 8. So I'm going to call this 8th degree, because once I get past 5 in this chart, there's no longer a special name. But if I were to reorder this in descending order, my lead coefficient should be that number in front of that 8th degree term, which I'll abbreviate that LC for -4 would be the lead coefficient. Okay, these problems at the bottom here, we're going to practice evaluating. This is a kind of an example of composition, honestly. I'm going to go ahead and circle, or actually highlight rather, our three terms. We have an f of x function, we have a g of x function, and we have an h of x function. Okay, now I think that you guys are probably all familiar with what f of 5 is asking you to do. Okay, the f is designating which function or equation you're going to be using. The 5 is a substitution. It's telling you that you're going to use function f, but you're going to substitute a 5 in for all of the x's in that function. Okay, so after you have done that, we then could simply use our calculator to kind of type that in, and we would get that f of 5, f composed of 5, comes out to be a 32. Okay, now it's really that same principle here when they say calculate f of 2a. Okay, so for f of 2a, they're still wanting you to use function f, but instead of plugging a 5, like we did in the previous problem, in for all of the x's, they want us to substitute a 2a in place where all of those x's were. Okay, now here's where some of those exponent properties from the previous video are going to come into play. Okay, remember we had one property that said it is okay to distribute the exponent on the outside of the parentheses and multiply it into all the exponents on the inside as long as what's inside the parentheses is all being multiplied together. Had this been a 2 plus a in the parentheses, then you would not be allowed to distribute that exponent. But in this case, we can distribute the exponent. That's going to make that a 2 squared and an a squared. Okay, if you look at the next set of parentheses here, this is just a 1 on the outside. So to distribute a 1 to the exponents on the 2 and the a is still going to leave that as a 2a. So you can almost drop these parentheses off and say to yourself, this 2 times that 2 is going to be a 4, and then you also just have this a that's going to get carried down. Okay, then we have our -3. We should change this 2 squared into a 4 and say we have 4a squared plus 4a minus 3 is what our answer would be for f of 2a. You'll notice the difference. If you are only plugging in a constant, your answer is a constant. However, if you're plugging in a variable, then your answer is like another expression that you've created. Okay, let's try this one. We're going to use g of 4a. So now we're going to come up and use equation g. I like to write out the equation first and just put an empty set of parentheses where all the x's are, and then come back and substitute a 4a in for all of those x's. Okay, similar situation here. I'm going to distribute the exponent there. Okay, however, in this situation, having a 1 out here, it doesn't really do anything when I distribute, so I'm going to imagine these parentheses aren't even here and just multiply the -5 and the 4 together and make that a -20a. Okay, in the end then, I should definitely square off that 4 and change that to a 16a squared. Okay. All right, I did example D for you. Now that is plugging in an entire quantity in place where the x is. And so I would like to look at example G. We'll just skip F here. Let's look at example G. Here they're saying do f of a plus 1. So we are asked to use equation F, but we're going to be substituting an a plus 1 in for each of the x's. And so again, this is where I like to just write out function F, but at the beginning, just put an empty set of parentheses where those x's are. Okay, then we can double back and in the parentheses put a plus 1 in place. Okay, now do you remember my warning earlier? When we were doing this, I said this one, it's okay to distribute the 2, and the reason is there's no addition or subtraction inside the parentheses. We said up here that had there been addition or subtraction, then you would not be able to distribute. Okay, do you see on this first term, we have addition in between those terms. So I'm not allowed to just say this would be a squared plus 1 squared. What I'm going to have to do for this is I'm going to have to FOIL that, okay? So what we'll need to do is we'll need to physically write the a plus 1 down twice, and that's what squaring something means. You're writing it out twice. Okay, here I'm going to go ahead and just distribute that 2 into the a and into the plus 1, and then we'll come back and we'll work on foiling together that a plus 1. Okay, we should be pretty good here with foiling. I'm going to go ahead and combine those two numbers at the end to a minus 1. And then you can see when we combine like terms, these are all of the a's. So I'm going to, it looks like that is going to be 4a. And then actually, these 1's end up canceling. And so my answer for f of a plus 1 is a squared plus. Okay, so we're going to go ahead on the back of this notes page here. We're going to take a look. Oh, you know what? Let's go back to the front real briefly here because I do want to look at these graphs of polynomials here with you. I want to draw your attention to the fact that the degree of your polynomial is always equal to the maximum number of times that your graph could intersect or touch the x-axis. Okay, now that was kind of a mouthful there. So let's look at some examples so that you kind of see this in action. So let's look at first degree. Okay, we know first degree, those are our linear graphs. Those are just our straight lines. The maximum number of times that a linear graph could possibly touch the x-axis is at most 1 time. Okay, that's the very, very most. And so what this is saying is the degree, what is 1 in this case, is always equal to the maximum number of times that your graph could possibly touch the x-axis. So you could never have a first degree function, a linear function, that would then come and cross your x-axis more than once. Okay, it's possible that it doesn't cross it at all. I don't know that that's actually the case here. Okay, maybe that's better to look at a quadratic. Let's go ahead and look at the quadratic. So we know that a quadratic is a degree of 2. Okay. So we know at most a quadratic or a parabola could cross the x-axis twice, but in the previous section we also learned that it's possible that it could just touch the x-axis in one location if it's touching at the vertex, or it's also possible that it doesn't touch the x-axis at all. So the degree isn't necessarily how many times it's going to touch the x-axis, but it is telling you the maximum number of times that it could. So it's either that number or less. And so you can see on a cubic graph, you know, there's always introduced like one more twist or turn to the graph when you increase another degree. There's like another U-turn that happens. Okay, here is a 4th degree. You can see it's crossing 4, and then we have a quintic that it's crossing 5. So it's just saying at most, that's how many times that it could cross. Okay, so we're going to take a look at some graphs here. I'm going to reference the calculator. Unfortunately, I cannot pull a calculator up here on the iPad, which is what I'm using, but I am going to make a couple of very short videos. If you are not sure how to do some of these things that we're going to be doing here today, then you can access on my webpage those very short videos that will have the calculator on it. So I'm going to talk first just about what the end behavior of a graph is. Okay, the end behavior is really just simply telling you whether your graph is pointing up or whether the graph is pointing down on the far left and right sides of the graph. So I'm just going to draw a quick graph here so that we get the idea here. Okay, you can see on the far left, the behavior on the left, the graph is going up, and then on the far right, the graph is going up. Now we have a special symbol that we use to mean far left or far right, and it's this symbol right here. When you see X with an arrow and infinity, I want you to think about an X-axis. Okay, we know that when you move farther to the right, the x values are getting larger, if you will, approaching infinity. And if you move farther to the left on the x-axis, then they're getting closer to what we would say negative infinity. So when you see the symbol x approaching infinity, that means right side, and when you see x approaching negative infinity, that means left side. And so when you identify the end behavior, this graph that I drew here, we could say, okay, as x approaches negative infinity, that's how you read the arrow. So this means as you look at the left side of your graph, then you look at the direction that the arrow in the actual graph is pointing, and that is telling you what the y values are doing. If my arrow is pointing up, then I'm going to say my y values are approaching infinity, because if you think of a y-axis, we know that as you climb up, the y values are getting bigger, so they're approaching positive infinity, but as you climb down, the y values are then approaching negative infinity. And so the end behavior always has two parts. You're describing what's happening on the left and then what's happening on the right. So then I would say, but on this graph as x approaches positive infinity, so now I'm looking at the right side, also, same thing, the y values would be climbing to positive infinity. Okay, we also just want to be comfortable with finding a max or min on a graph. Okay, we know that the maxes and the mins, and I'm just going to use this graph that I sketched here. This would have actually 2 mins and 1 max. And if you're not sure how to find a max or min on the calculator, there's a great feature that's very, very easy. Please go and watch a super short, just a couple minute video on my webpage under the tab TI-84 videos that will show you how to use your calculator very easily to find a max or a min. Okay, the other thing you're going to be asked to do is find the y-intercept. The y-intercept can simply be found by plugging a 0 in for the x's. If you think about the y-intercept, that's always a point on the y-axis, and what all of those points have in common is they all have a 0 as the x-coordinate. Okay, and we're going to do this here today. I'll do this with you. I just want to talk through each of these terms. And then the other thing are what we call the zeros of your function. The zeros are the x-intercepts, and we are definitely going to be using our calculator to find the zeros. Again, I'm going to have a very short video on my webpage under that same tab, TI-84 videos, that will walk you through how to go to second, calculate 0, and kind of calculate the x-intercepts of your graph, okay? So we'll come back and talk about odd and even in just a minute. Let's take a look at these last 3 problems right here on your notes page. EB is short for end behavior. So I've got a couple blanks here. The first blank here is you always going to be just saying as I look to the left and then as I look to the right. So our way of saying as we look to the left is to say x with an arrow approaching negative infinity. Okay, so as we look to the left of this graph, we are going to be looking at which way the arrow is pointing. It's pointing down, so that tells me the y values are approaching negative infinity. And then we'll say as we look to the right, so that's as x approaches positive infinity. I'm looking over here now. I see also the arrows are going down, so I'm going to say y approaches also negative infinity. Okay. I'm going to count the number of zeros. We're going to skip odd and even just for a moment. Zeros, please remember zeros just means x-intercepts. So all they're wanting you to do is simply look at this graph and just count up how many times does this touch the x-axis. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So there are 10 zeros there. Okay, let's do the end behavior for this one as x approaches negative infinity. So I'm looking to the left. Looks like now the arrow is going up. I'm going to say the y values approach positive infinity. And then as I look to the right, so I fill in as x approaches positive infinity, looks like the y values are now going down, approaching negative infinity. Again, I'm going to count the number of zeros. That's simply the number of x-intercepts. This one has 5. And then we'll go back and we'll take a quick look at just what is even and odd functions. We're actually not going to use this explanation right here. Even and odd functions, what you're going to do is you're going to look at the graph. Even is pretty easy to tell. Okay, even, what you're looking at is if you look at your graph and it feels like the left portion of your graph looks like it's been reflected, it has to be directly across the y-axis though. Okay, not just a reflection vertically, but it has to look like if you folded your graph, I'll just give you an example right here. If I folded my graph on the y-axis, would the right side match up with the left side? This graph I just drew here is an even function, but if I were to place the parabola here, now this is not an even function, because if I fold right here, I wouldn't have, there's nothing even on this side. Okay, so let's go back and look at these three graphs and say, do any of these look like they would be even functions? If we folded it down along the y-axis, is what's on the left going to be a mirror image of what's on the right? And the only one that looks like that is example A. Okay, so now let's look at what an odd function is. Okay, an odd function is, and here's the easiest way, it's if you took the left side of your graph, okay, so just the part to the left of the y-axis, and you flipped it down over the x-axis. If you took the left side and flipped it down over the x-axis and then examined the graph, if the graph then feels like it's even, meaning then it's symmetrical across the y-axis, that means your function is odd. Okay, I'm going to use example C as an example because this is an odd function. If I took what's on just the left side, so just this part right here, and I flipped it across the x-axis, it would then land about like that. Okay, so after I've reflected it across the x-axis, if now that reflected piece looks like it is a reflection over the y-axis to this side, that means the original graph is odd, and that's the case on this one. I would say that's odd. Now, it's also possible that your graph is neither. Okay, this one definitely does not look like it's reflected across the y-axis. It also doesn't look like if I took this left side and flipped it over the, the x-axis, that it would then look symmetrical across the y-axis. So I'm just going to circle neither for that. Okay, again, if you are unsure at all how to calculate the zeros, the x-intercepts on a graph, or how to find the max or